The last chapter or last day of Unit 8, we're talking about proportionality theorems and the midsegment of a triangle. If you remember previously when we were in Chapter 6, you saw the word midsegment on a card sort we did, and I told you to ignore it for right now. Well, now we're not going to ignore it. We're going to talk about a midsegment. But we're also going to talk about proportionality of the sides of triangles. Now, proportionality means that we're going to set up some fractions over and over again. The proportion that we set up before was always new divided by old, but since we're not dealing with two separate fractions, but one triangle with multiple markings on it, we're now going to call it like top over bottom or left over right. But I'm going to stick with saying tops over bottoms. So if we notice in the triangle proportionality theorem, it says if a line parallel to one side of the triangle intersects two other sides, then it divides the two triangles proportionally. So we're making sure that we notice that these two triangles are parallel. They have the little arrows, not triangles, lines, that those lines are parallel to each other. So they have the parallel symbol, which is a little bitty arrow on the lines. If that's the case, then what we know for this triangle is that the green side over the green side, so the first green little segment, RT, divided by the second green little segment, TQ, the tops, will be exactly proportional to the bottoms, RU over US. So we have the two parts of the green divided by the two parts of the blue, or equal to the two parts of the blue. Does that make sense? So when we solve a problem like this, which in oh my gosh, my words are not flowing today. Problem 1, it asks you to determine whether AB is parallel to XY. Well, my theorem that we just went over says these two lines will be parallel if these are proportional. So we set up our proportions, green over green equal to blue over blue, and we solve. Now, if you'll notice, there's not like anything to actually solve because I fill in all numbers for both the greens and both the blues. The ZA part of this is 3, the AX part of this is 4, ZB is 4, and BY is 5. So when I fill this in, I have complete fractions, no variables. I still cross multiply, and then I compare these numbers. 4 times 4 is 16, 3 times 5 is 15. Are those numbers equal to each other? That was a legitimate question. Are those two numbers equal to each other? No, so these are not proportional, so they're not parallel. If we set up the entire problem number 2, keeping the greens with the greens and the blues with the blues, the letters we would use for this one would be ZB over BY equal to the blues, ZA over AX. Do we see that setup? The green sides, blue sides. To verify that the two lines are parallel, we just need to cross multiply the numbers for each of those sides. ZB is 6, BY is 4, ZA is 7.5, and AX is 5. When we cross multiply these, and this is where your calculator comes in handy, what is 4 times 7.5? Beep, beep, beep. Let's type it in on our calculators. We should get 30. And then what is 6 times 5? Also 30. Are those numbers the same? If those numbers are the same, then we say yes, the two lines are parallel because their sides are proportional. So if we were going to edit this image, we would add the parallel little lines here to show that these two lines are parallel. So we can use this idea of proportionality to not only answer if two lines are parallel, but find missing side lengths. So this time, when we set up our proportion, we will have a variable. If we're looking at the color scheme here, we have AE and ED are my greens. We have AB and BC are my blues. But when I fill in these numbers, AE is 5, ED is 10, AB AB is missing. So we put an X right there. BC is 6. When I actually cross multiply these problems, and I'm going to draw arrows over this instead of just little lines. When I draw my arrows, I end up with 10x equal to 30, which is an easy solve, and we would say that x is equal to 10. X is equal to 3, which means the side length AB is equal to 3, since that's the missing side length. Questions about this before we go to one that requires a little bit more algebra? No? Fabulous. Let's do one with a little bit more algebra. We've been prepared for these before. We've seen them. Help me set them up. Let's go greens, then blues. So my green side lengths would be named what and what? CB divide by BA. And we would set that equal to the blues, which are what letters? CD, DE. At this point, we just need to fill in the missing information, the numbers from each of the side lengths, which means for CB, we put 30. For BA, we put this entire expression, x plus 7. On the other side, we put 25 for CD and 15 for DE. When I cross multiply here, I actually have to remember to distribute, because this cross multiplication is not easy. 25 times a binomial would be 25 open parentheses x plus 7 equal to 30 times 15, which fast forward that math, is 450. We've seen this kind of problem before. What did I tell you you needed to do with this number in front of the parentheses? Do the distribution arrows. So we're going to multiply 25 times x and 25 times 7, which again, I'm going to fast forward that math. This is 25x plus 175 equal to that 450. At this point, you can use inverse operations or the box method to solve for x. I know we're most comfortable with the box method, so we'll draw our boxes. I'm going to zoom in so I have some more room. Draw our line, draw our boxes. How many terms have x in them? Just one. How many terms don't have x's? 2. So our setup looks a little weird. We've got one box on the left and 2 boxes on the right. We drag and drop our numbers. 25, no change. 175, definitely change. 450, no change. The 25 just drops down because there's nothing to add it together, but we add negative 175 and 450, which again, I'll fast forward the math, is 275. What's that very last step for the box method? Divide. We're going to divide by 25, divide by 25. We get that x is equal to 11. Hooray! I know I ran out of space there. I'm so sorry. Are we done with this problem? No, because it didn't ask me for x. What did it ask me for? AB. Okay, we got that x is equal to 11, and AB is x plus 7, which means we're really just trying to find AB. Let me make that green, sorry. AB is really just 11 plus 7. So AB is 18 units long. We had to use this number, 11, that we solved for x. So there are times you will take your answer x and plug it in to answer a different question. I don't think we've done that yet, but we've done that in other units. One thing I kind of overlooked in these problems is that we're able to do these proportions because these lines are parallel. So you have to look for these little arrow markings to be able to do this. If you don't have the arrow markings, technically you don't have enough information to answer these questions like this. The bottom part here is a new theorem. It's called the triangle angle bisector theorem. In this theorem, if a ray bisects, which means cuts in half, an angle of a triangle, then it divides the opposite side into segments whose lengths are proportional to the lengths of the two other sides. So we're still going to set up proportions, but this time it's not along the sides. This time our proportions, still by color, are blues equal to greens, but my greens are now both sides, and my blues are now the third opposite side. This is because of this angle bisector here. So we're looking for these markings that this angle is the same as this angle. But then we got proportions, and we've been solving proportions really well in the last few lessons, so I'm not that worried about the math here. We're going to follow along with the example that Ms. Caldera did for us, and then we'll do our own. It says use proportionality to find the missing sides. These sides don't have names, so we're not going to use letters, but we'll just use the markings and the highlighting. So in this problem, we have blues equal to greens. The blue numbers make one fraction. The green numbers make another fraction. We have to make sure, though, that the sides that touch each other are on tops and sides that touch each other are on bottoms. But then we set up and solve a proportion. 5 times 9 is 45. X times 15 is 15x. Divide by 15. You get that the missing side length is 3. Can we do a problem together now that we have a nice example? In number 6, it says find the missing side. Notice that it wants this entire thing, which means I'll have to add this segment plus this segment. But I don't know what this one is, so we're going to put a variable right there. We're going to put an x so that we can eventually find it and then add it to 6. If we set up our proportions, we'll go blues then greens just to follow suit. So we have blue 6 over x equal to the greens. Now, on my green one, what number do I put on top, 12 or 8? Ooh, I heard both. So we want to keep the sides that touch on the same side, either tops or bottoms. So 6 is on top. What touches 6? 12 goes on top. And then the 8 touches the x, so the 8 is on bottom. We cross multiply and solve. 12 times x is 12x. 6 times 8 is 48. If you could finish this one for me, I'm going to answer the phone so y'all finish this problem. The step I stopped on, you would just need to divide by 12 on both sides to get the x by itself. We get that x is 4. Now, is that my final answer here? No, because I asked for the entire side length over there. So that entire blue side length is going to be 6 plus 4. My missing side length, my question mark side length, is going to be 10. It doesn't have a name, but we put a question mark there, so I like putting my question mark in my answer. That missing side length is 10. Continuing on with our idea of proportions, there are still more ways we can set up proportions to solve problems. Like on the back here, it's called the 3 parallel lines theorem. In this theorem, if 3 parallel lines intersect 2 transversals, then they divide the transversals proportionally. So we're not dealing with triangles here necessarily, but if we notice that we have 3 marked parallel lines, pow, 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 all have the little arrow indicating that they are parallel, then we can take the little segments in between them and make them proportional, meaning the green UW and green WY, that's this guy and this guy, will be proportional to VX and XZ, which is here, VX and XZ. So again, it's all about proportions today. All of these different ways that triangles or line segments are proportional to each other. You see the example that we did for you. To find BD, we set up the exact same way. We have our green AC over CE equal to the blue BD over DF. But we're trying to find BD because we don't know it. So when Ms. Caldera did this problem, she left an X where BD would go, and filled in the rest of the numbers. She did 40 times X, 16 times 30, and then divided by 40. So she got that x is equal to 12. So to answer the question, she said BD is 12 units long. Very familiar, still a proportion. We're just grabbing the numbers from different relationships among triangles and now triple parallel lines. In number 8, we know that these are all parallel because they all meet at a 90-degree angle to that one transversal. So they're going the same direction. So we know we can use this theorem. To find GM in this theorem, which again, notice GM is this entire distance, we are going to set up our proportions by color. We would say GJ over JM is going to be equal to the blue HK over KN. We fill in what we know. GJ is 16, JM is, I don't know, okay, X. HK is 15, KN is 18. So I popped an X right here for JM since I actually don't know that distance. We cross multiply and we solve. 15 times X is 15X. 16 times 18 is 288. What's that last step? Divide by 15. We do get a decimal here, and it's a cute decimal, so we'll leave it and not put it in fraction form. It's 19.2. Great. Does this answer the actual question? No, because remember I asked for GM. GM was the entire distance of the green part, so from G to M, which means GM is going to be equal to 16 plus that value X we just found, the entire distance. So if we do 19.2 plus 16, we get 35.2 units. So that's the actual answer here. Make sure you know what the question is asking so you answer the right question. So it's all, again, all about proportions. The first 3 theorems we use today is just getting your proportions set up correctly and solving correctly with maybe a little bit of algebra tossed in there. The next little bit of notes is going to introduce a new segment for a triangle. So this kind of goes with the ideas of Unit 6 that we did, all of those midpoint or midlines, altitudes, perpendicular bisectors, angle bisectors. Now you also have a midsegment. Let's highlight the word midsegment for ourselves. A midsegment of a triangle is a segment that connects the midpoints of 2 sides of a triangle. So if you notice, in the triangle I have highlighted for you, we've got this line in the center of our bigger triangle, and it is specifically cutting the triangle so that this side and this side are equal, this side and this side are equal, cutting them directly in the center of each segment. So if a segment connects the midpoints of 2 sides of a triangle, then the segment is actually parallel to the 3rd side. And more importantly, that segment is half as long as the 3rd side, which is going to allow us to do a lot of algebra very quickly to solve for these different lengths. So in this image, our midsegment is segment DE. Since I know that it's a midsegment, I see the markings to tell me it's a midsegment. I know that side length DE is going to be exactly parallel to AC. Based on the theorem as well, it tells me that DE is going to be half as long as AC. Ew, but I don't love dealing with fractions. So the formula you're actually going to use is that AC, your purple side, is going to be equal to 2 times DE. So that we're multiplying by 2 instead of by a half, because I think we're more comfortable multiplying by 2 than multiplying by fractions. So we're going to multiply by 2 to make the short side equal to the longer side. So if you wanting to like make yourself a huge note here, I would like put some exclamation points on this. This is what we're going to use the most. Super important. So if you notice, we've set some problems up like this. In problem number 9, we're finding the value of x, but we've set it up so that we say BC is equal to 2 times DE. So when we fill in our stuff, BC is 28, DE is x, so we say 2 times x. Solve for x is really easy. We divide by 2, and boom, we have the value of x, which is also, in this case, the length of DE. If we do number 10, we know, and this is how we're going to write it, we're going to say BC, the longer length, is equal to 2 times DE, that shorter length. So let's fill in what we know. What is BC labeled as? Is there a number on there? No, what's there though? X, so we're just going to put X there. That's okay. Then we're going to do 2 times DE. What is DE? What is DE labeled as? 15. Oh, snap, I don't even have to solve anything. I'm just evaluating. What is 2 times 15? 30. So X is equal to 30, which is also, coincidentally, the length of BC. Double the midsegment. 15 times 2 is 30. This question also has a part 2. It says, yeah, but what's Y? This is a midsegment. Midsegment means that AD and BD are the same length, and it means that AE and EC are the same length. So how long is Y? Oh wait, what has the same markings as I put on the Y length? 9. So that whole side is going to be 9 and 9, because if it's a midsegment, it cuts it perfectly in half. So if one side is 9, the other side is 9. So a thing to help you out here, if you think midsegment, midpoint. They both start with mid, which is really nice. Midsegment, midpoint. Midpoint is halfway, so they're the same on each side. Midsegment, midpoint. Okay, last problem we're doing with me before you get to stop listening to my voice is problem 11. It's a two-parter because I want X and I want the length of DE. Now we've set it up for you slightly. We said, all right, for this problem, it should say BC. Let's edit that. This should say BC. BC equal to 2DE. That's going to be the formula you use all the time. Long side equal to double the short side. But when I fill this one in, I actually end up with a different type of equation. BC is labeled as 2x plus 24. DE is labeled as 3x plus 8. Before I do the box method or inverse operations, what do I have to do? Distribute. We got to multiply. So this becomes 2x plus 24 equal to 6x plus 18. I mean what? 16? Now we set up our box method and solve. We're going to do this one together. How many x terms do I have in this problem? 2. How many non-x terms called constants? 2. When we drag and drop, we'll have 2x over here, 24 all the way over there. Cross the line, change your sign. Oops, 6x, cross the line, change the sign. And 16 drops right down. We've seen this enough times, I can do this a little quick, yes? I add the top numbers to make the bottom. 2 plus negative 6 is negative 4. Negative 24 plus 16 is negative 8. Divide by negative 4. Divide by negative 4. We get that x is equal to 2. Huzzah! We've answered the first part. To answer the second part, when I ask you for DE, We know that DE is equal to 3 times x plus 8. What do I put now in the place of x? 2. So we're just calculating 3 times 2 plus 8. 3 times 2 is 6. 6 plus 8, 14. So again, be sure you know what the question's asking for. If it had just asked for x, we would have been done when we said 2. But because it asks you to plug that number in, you have to answer with both. So be wary with that on your test we're taking on Monday, whether I'm asking for just x or for the side length.